Hello everyone. The topic for today's lecture is objects and references. This is a conceptually challenging topic. If you have any follow-up questions, I would encourage you to attend the live stream session to get those clarified. There is a template notebook file that you can download to follow along with today's lecture. I will not be using the template notebook file. Please feel free to download and use it. We are going to get today's lecture started by going through a mini quiz. Please pause the lecture video here and go through these questions and provide your answers as a comment in the comment section. Question A is asking what is the type of empty curly braces? Recall that we'll be creating a dictionary when we specify empty curly braces. If there are items within the curly braces, how can you differentiate between a set and a dictionary? You'll have to look within the items. If there is a colon separating the key and the value, then you have a dictionary. If there is no colon, then you have a set. Let's go through question C, which is asking which type is immutable. Recall that list and dictionary types are mutable because you are allowed to make changes to values stored within those types. String, on the other hand, is an immutable type. Question B is stating that S is a string and L is a list. Then you have two lines of code between which you are supposed to pick one that will definitely fail. Line 1 here is guaranteed to fail. That's because S is a string. Strings are immutable. So you cannot use this syntax to update the character at a certain index position within the string sequence. Line 2 may or may not execute. Let's consider scenario 1 where line 2 will execute successfully. Let's say that list L contains 100 items and string S contains 5 characters. This particular line of code will run. That's because len of S will give you 5. Recall that you can use this particular syntax to update the item at an existing index position. How do we know there is an item at index position 5 within L? That's because L contains 100 items. Let's consider the alternate scenario where string S contains 100 characters and list L contains 5 items. Then this particular line of code will fail. That's because len of S will give you 100. Recall that you cannot use this particular syntax to insert a new item into a non-existing index position. How do we know 100 is a non-existing index position within list L? That's because list L only contains 5 items. We are going to use this crazy nested data structure diagram from the previous lecture to understand the concept of objects and references. Whenever you have an arrow, the pointy end of the arrow is going to point at an object. The non-pointy end is going to be a reference to that particular object. So far, we have been mentioning that variables store data types and data structures. That is technically not correct. Variables store references to objects, which in turn store data types and data structures. Objects reside within heap memory. Why is it called a heap? That's because you have a jumble of all the objects. Variables, along with frames, reside inside stack memory. Why is it called a stack? That's because we are stacking one frame on top of another. Let's go through observations with respect to objects and references. Observation 1 states that objects have a life of their own. Let me give you examples to go through this particular observation. Let's consider this list object here. Observe that there are two different variables which store references to this particular list object. Both of those variables are part of different frames. Clearly, this object has a life of its own beyond these frames. Let's consider these two list objects here. Observe that there are no variables that contain references to these list objects. There are only references to these list objects from inside this dictionary object. Observation 2 here is mentioning that in this particular version of this diagram, there are two kinds of objects which are dictionary object and list objects. There are other possible objects. I'll give you example for that shortly. Observation 3 is stating that references to objects can show up as part of two places. The first place is within a variable. An example would be the Webster variable, which is storing reference to this particular dictionary object. The second place would be within other objects. An example would be this particular list object whose reference is stored inside this dictionary object. In Python, all primitive types are considered as objects. What are primitive data types? Those are going to be the four data types that we initially covered. Those are integers, floats, Boolean values, and string values. There are other programming languages which do not consider primitive data types as objects. Python differs from all of those programming languages. Let's compare and contrast the previous version of the diagram with the current version. Observe that in the previous version, we directly mentioned the integers 8 and 9 within the list object here and the strings zebra and mammal within the dictionary object. The correct representation would be to draw an arrow from the list index position and from the value corresponding to the dictionary key pointing to the corresponding integer and string objects. As you can see, this diagrammatic representation can get very cluttered if we were to use arrows for every primitive data type. So we are going to prefer the previous version, even though in Python everything is considered as an object. Why do we need this more complicated mental model? Up until last lecture, we did not learn about objects and references and we were doing fine. That's because this complicated model is going to enable us to create custom types, which is pretty cool. How can we compare objects and references? Can we just use the double equal to comparison operator? The answer is no. We are going to learn about a new comparison operator called is. How can we copy objects to create new objects? We are going to learn answers to all of these questions as part of today's lecture. Let's get started by learning about the tuple data structure. You'll grasp tuple data structure pretty easily if you have a good understanding of the list data structure. Recall that we use square brackets to define a list data structure. We are creating a variable called nums underscore list, which is going to store a reference to this particular list object, which contains three items here. How can we create a tuple? You need to use parentheses instead of square brackets, and that's going to enable you to create a tuple object and add a reference to that inside the variable nums underscore tuple. What is the difference between a list and a tuple? Unlike lists, tuples are immutable. Recall that lists are mutable. Let's go through operations that you can do with a tuple and which you cannot do with a tuple. Just like you can perform indexing to extract a certain item at a specific index position from a list, you can perform indexing to extract the item at a certain index position with a tuple as well. Unlike extracting item using indexing, you cannot use tuple to update the item at a certain index position. That's because tuples are immutable. So when you say nums underscore list of 0 equal to 99, that will succeed. But when you say nums underscore tuple of 0 equal to 99, your program will crash with an error stating that you have type error, tuple object does not support item assignment. All that you need to understand about this type error is that tuple is immutable. Why exactly do we want tuple data structure? It feels like it is a worse version of the list, correct? Let me give you a twofold reason for that. Let's say that you want to store certain kind of data which will never change. An example would be the hurricane data set. A hurricane has already come to pass. Its speed and number of deaths can never change. In order to avoid bugs within your program where you accidentally change some data which should not be changed, you can use the tuple data structure as opposed to a list data structure. The second reason is that in certain cases, it is required to have a tuple as opposed to a list. An example would be configuring a key within a dictionary. I mentioned that I'll discuss the concept of immutability of dictionary keys as part of a later lecture. As promised, here is an example. Let's say that we are trying to define a building's dictionary with certain lists as keys. That's going to fail with the type error stating that unhashable type list. I'm not going to go into details of hashing. All that you need to understand here is that you're using list as a key within the dictionary, which is not allowed because lists are mutable. You can replace those lists with tuples instead, and now this particular dictionary creation will succeed. That's because tuples are immutable. Keep in mind that you're only allowed to have immutable types as keys within your dictionary. Let's do a quick recap of the parenthetical characters. This is the third overloading situation that we are discussing for the parenthetical character with respect to the tuple data structure. Recall that we have already used parentheses to specify order within an expression or to define or invoke a function. When you have a comma within your parenthetical character, you will be defining a tuple. I'll not be doing a recap of square brackets and curly braces. Feel free to use this slide to do that on your own. Here is a tricky question. When you mention 1 plus 2 within parentheses, are you creating a tuple or are you mentioning that as order specification for that particular expression? Turns out that you're mentioning the order specification when you say open parenthesis 1 plus 2 close parenthesis. If you want to create a tuple of size 1, you'll have to mention that expression and add a trailing comma. That's how you can create a tuple of size 1. I'll wrap up this lecture video here. In the next video, we'll learn about name tuple and record class.